We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello everyone, my name is Hiren Patel, working as Assistant Professor in Mahatma Gandhi Institute of Technical Education and Research Center, NAVSARI. In today's lecture, we are going to discuss about multiple evaporator and compressor VCR systems. As we have seen in previous videos that every system works on a single evaporator. That single evaporator have to carry the total or entire load, but in many refrigeration installation different temperature are required to be maintained at various places in the plant, like hotels, large restaurants, institute, industrial plants, cold storage, etc. For example, if there are supply of fresh fruit, fresh vegetable, fresh meat, frozen products, dairy products, all are required to store at different temperatures. So when there is requirement of storing different product at different temperature, the multiple evaporator and compressor systems are good for that, and they give the satisfactory control conditions. So there are different kinds of multiple evaporator and compressor systems that are listed over here. So if we can see, there are 8 type of different systems are there with multiple evaporator, single or multiple compressor, individual or compound compression, etc. So during this lecture we are going to see the different kind of systems. So starting with the first, multiple evaporators at same temperature with single compressor and expansion valve. So in this system you can see that there are 3 different evaporators, only one compressor, one condenser and single expansion valve. So this system is generally used when the number of loads such as food product or other materials required to be kept at a same temperature, then this system is useful. So here, as we can see that there are 3 types of load, that is Q1, Q2 and Q3. So each and every load are on different evaporator, but the required temperature is same. So we can also see it in pH chart that only single compression is there, 1 to 2, and the cooling is 4 to 1, but it is in 3 different evaporator at same temperature. So from the pH chart, mass of refrigerant that is required to be circulate through first evaporator, that is M1. So if we consider different mass like M1, M2 and M3 required at 3 different evaporators, then M1 will be the 210Q divided by H1 minus H4, same as M2 is 210Q2 divided by H1 minus H4, and M3 is 210Q3 divided by H1 minus H4. So Q1, Q2 and Q3, these are the different loads at different evaporators. So total mass of refrigerant that required is M equal to M1 plus M2 plus M3. So total work done will be m1 plus m2 plus m3, or we can say m into h2 minus h1, and refrigerating effect is m h1 minus h4, and COP is refrigerating effect divided by the work done, that is W. So here the total COP is H1 minus HF3 divided by H2 minus H1. So this is the simple multiple evaporators system, but this system is only useful when the temperature required is same for each and every evaporator. So only single expansion valve, single condenser and single compressor is there. So work done will remains constant for this system. So this is the simple multiple evaporator system. So second one is little bit modification of this system, that is multiple evaporator at different temperature with single compressor, individual expansion valve and back pressure valve. So this system is utilized when the temperature required at different places are different. So different products required to store at different temperature, then this kind of multiple evaporator system is used. Here we can see that there are 3 evaporators, and for that 3 evaporators individual expansion valve is provided, but compressor and condenser is single. So in this arrangement there are 3 expansion valve with back pressure valve. So same as previous one, there are 3 different loads for 3 different evaporators, that is Q1, Q2 and Q3. So here in pH chart we can also see that there is difference in temperature for different evaporators. So if we calculate the mass, okay, we have seen that in previous system the mass is calculated for single evaporator, same means same temperature, so it is between 1 and 4 point. But in this case the temperatures are different. For evaporator 1 it is between 1 to 10, for evaporator 2 it is between 8 7, and for evaporator 3 it is between 5 and 4. So for evaporator 1, M1 is equal to 210Q divided by H11 minus H10, M2 is 210Q2 H8 minus H7, and M3 is equal to 210Q3 divided by H5 minus H4. So here the difference of enthalpy is different for each and every evaporator. So that is the difference between previous and this system, and H1 will be calculated from this equation, as H1 is the common point of all, that is the entry of compressor. So the condition of the refrigerant after mixing and entering into the compressor, here we can see that all the refrigerant coming from evaporator are mixed at entry of the compressor. So the enthalpy will be different. So work done is same as previous one, same as power, but the difference in refrigerating effect is that for each and every evaporator the mass and enthalpy difference are different. So refrigerating effect is M1 H1 minus H11 plus M2 into H8 minus H7, plus M3 into H5 minus H4, or 210 Q1 plus Q2 plus Q3, and COP is refrigerating effect divided by W. So COP will remain same, equation remains same, that is refrigerating effect by work done, but the difference in refrigerating effect is there for each and every system. So this system is for different temperature requirement. Okay, now next system is multiple evaporator at different temperature with single compressor and multiple expansion valve and back pressure valve. So there is little bit difference. The difference is there in previous system, for different temperature with single compressor, every evaporator has individual expansion valve. So every expansion start in same enthalpy point, that is HF3, or same point, that is the exit of condenser point. But in this system what happens, the multiple expansion valve is given, that first refrigerant expanded in expansion valve 3, then it is distributed in two parts, one portion goes to evaporator and second portion goes to next expansion valve. So every time when refrigerant passing through the expansion valve, it goes to the saturated liquid, so it converted to saturated liquid, and each and every expansion valve after expansion it has some of the dryness fraction, that is given here, that is x4 x7. So here after expansion from E3, here there is the point where it has some of the vapor contained inside the liquid refrigerant. So it is also occur at this 7 point and 10 point. So here instead of individual expansion valve, the expansion valve is given in multiple options. So expansion occurs in each and every expansion valve one by one by forwarding the refrigerant. So after 3 expansion, the refrigerant passes from the first evaporator. After 2 expansion, refrigerant is passing from the second evaporator, and only 1 expansion, the refrigerant passes from the third evaporator. So the major difference is in temperature. So refrigerant which is reaching to the first evaporator has the maximum COP, or we can say the lowest temperature, and in second and third in increasing order the different temperatures are there. So here also for the different evaporator there are different loads. So if we consider, that is Q1, Q2 and Q3. So if we see for the mass, that mass of refrigerant required to be circulated through the first evaporator, or we can say lowest temperature evaporator, that is EP1, here indicated by EP1, that will be M1, that is 210Q1 divided by H11 minus H10. Mass of refrigerant that is required to be transferred or circulate through second evaporator, or we can say intermediate evaporator, that is M2, 210 Q2 divided by H9 minus H7 kg per minute. But in this, what happens, this in this evaporator, it is also supplied with the vapor formed during the expansion of mass that is forwarded in E1. So that vapor is also goes inside the second evaporator. So the mass of that vapor, that is calculated by M2 dash. So M2 dash will be given by the equation Me1 into X7 divided by 1 minus X7, that is the dryness fraction available at that point here, at this point. So total mass that is required to circulate through second evaporator is this, that is M2 plus M2 dash. Same as M3, that is 210 Q3 divided by H6 minus H4. Same as here also in third evaporator, here it is also supplied with the sum of the vapor that is generated during the expansion of, if we say this is Me1, Me2 and Me3 mass for evaporator 1, evaporator 2 and evaporator 3. Then Me2 and Me1 is also expanded through this expansion valve. So they both masses are generating the vapor, and that mass of vapor is calculated by this equation, that is M3 dash equal to Me1 plus Me2 into X4 divided by 1 minus X4, that is the dryness fraction available at the point 4, and total mass that is calculated by M3 plus M3 dash. So total mass that is circulated through the system, that is M is equal to Me1 plus Me2 plus Me3. Here also the compressor is single, so all the refrigerant coming out from the individual evaporator are mixing before the entering to the compressor. So the H1 will be given by the equation, that is this work done, that is M into H2 minus H1, refrigerating effect, that is 210 into Q1 plus Q2 plus Q3, and COP, that is refrigerating effect divided by work done. So this system is useful when the temperature difference is major compared to the previous system. In previous system the difference of temperature is same, but the range of temperature is different. But in this case the range of temperature is also different and temperature is also different. So where lowest temperature is required, then this multiple evaporator system is used. Next one is multiple evaporators at different temperature with individual compressor and individual expansion valve. So here in this system, instead of single compressor, multiple compressor are provided for each and every evaporator. EP1, EP2, EP3, there are 3 compressors, C1, C2 and C3, and also 3 different expansion valve. Only condenser is single. So we can see in pH chart 3 different compressor are there, and for that 3 different compression ratios are there and 3 different temperatures are there for the compressor as well as evaporators. So this system is utilized when the power required is low, or we need to require lower we can say less amount of material. So when the evaporator size are less and we require small amount of storage capacity, then this type of systems are used. So here same as Q1, Q2 and Q3, three loads are there. So for that, mass M1, M2 and M3 need to be circulated from these three different evaporators. So if we calculate mass, then M1 is 210 Q1 divided by H1 minus H11, same as M2 210 Q2 divided by H3 minus H9, and M3 210 Q3 divided by H5 minus H8. Here in this case, compressor are different. So for individual evaporators, the individual compressor are provided. So the power required are different. So for first evaporator, power is M1 H2 minus H1 by 60, same as P2 M2 H4 minus H3 by 60, and P3 M3 H6 minus H5 by 60. So total power will be P1 plus P2 plus P3, same as total work done will be W1 plus W2 plus W3, that is M1 H2 minus H1 plus M2 H4 minus H3 plus M3 H6 minus H5. And refrigerating effect is same as 210 Q1 plus Q2 plus Q3, and COP will be refrigerating effect by work done. So these are the four different kind of multiple evaporator systems are there. Next four system we will see in the next video. Thank you for watching.